Hi everyone, welcome to lecture 4. So we have some more announcements. Homework 1, again, still not released. Apparently there were some difficulties in merging the two homeworks, but I've been told that that would be done by 2 p.m., so probably very soon. Is it up?
I think so.
As of, when did you check? Okay, I think also there was a miscommunication actually on the back end, and someone posted the old homework 1, the unmerged version, and that came down, so that might be what that was. But yeah, the actual homework not posted yet, still due next Wednesday, so you'll still have plenty of time to do it. Reminder, limited submissions on the instant grading. If you run out though, you can go to office hours and get them reset. So there's, yeah, unlimited tries as long as you're willing to do that. Another note that I haven't brought up before, there are some tutorial videos on edX, some that were already existing. They are walking through step by step the execution of the algorithms that we covered so far, depth first, breadth first, and A-star search by Professor Peter Abiel. And then we ran out of time at the end of lecture yesterday, and the material that we weren't able to cover is not necessary for today's lecture. So rather than cut out what we could cover today, I made a little tutorial video on that goes through that proof in a little more detail than we would have had time to in lecture, and hopefully that will be sufficient. I really recommend watching that. The slides are still there for reference, so you're welcome to read the slides, and if you've done a lot of proofs in the past, that might be enough for you to understand everything that's there, but this goes through in a lot more detail. On that note, I want to make it a statement about where lecture fits in the CS188 ecosystem. So up to this point, lecture has really been the only thing. As of yesterday, most of you have been to a discussion section and been in the smaller setting where you're able to ask more in-depth questions and get more personalized help. My experience is mostly in that setting, and so I'm carrying some tendencies of really wanting to cover the details and make sure everyone gets it right now, when what we should be doing in lecture is just giving an overview, and you can get into the details later on Piazza or in discussion section. So that's why we've been running out of time. I'm trying to rectify that. We'll go into a little less depth on the proofs from here forward. And last point, finally, the office hour schedule has been posted. It's on Piazza, and the reason it's on Piazza is before going, you should always check that post. If there are any weekly fluctuations in people's schedules, that will be the single source of information about that. Any questions about logistics? Great. So the topic for today is constraint satisfaction problems. So we're stepping a little bit out of search, which we've been doing for the last 2 days. But the reason this is next is we'll see that this is actually just another broad class of problems that actually are a specific case of search. What we're going to do is start with first defining what a constraint satisfaction problem is, showing how we can apply the search algorithms we already know to those, and then how we can exploit some extra structure that we know from this particular kind of search problem. Because it's a constraint satisfaction problem, we can tweak the search algorithms to be optimized for these and perform a lot better. So before we mathematically define it, I want to introduce intuitively this example. You may be familiar with this if you are drawing a map, and it's a political map that has all the countries. Every country has to be a different color from the one next to it so that when you look at the map, you can see where the borders are pretty easily. So that's what this problem is for each one of these states, you need to color it to be a color. For the sake of today's examples, we're going to use 3 colors, red, blue, and green, so that no countries are the same color as the one right next to them. So this may seem a little contrived, maybe not, but on a day-to-day basis, you don't do a lot of coloring maps. But we'll see that the structure that we're going to use to examine all CSPs is more visible in this. You'll see what I mean when we talk about constraint graphs pretty soon. And so this is a pretty good example. So first talking about, like I said, search algorithms. Normally we treat the search problem as a black box. We have access to the set of states and a successor function and a goal test. And those are the only things that we use when executing a search algorithm. If you look back at the pseudocode for tree search or graph search, every single step that's the only way it's going to interact with the actual environment, is through those three functions. But now, with a constraint satisfaction problem, we're going to actually have some knowledge about what's going on inside that successor function. So here's going to be our definition. There are three pieces. Each constraint satisfaction problem is going to have a set of variables. It's going to have some domains, a domain for each of those variables, and a set of constraints. So for the map coloring example, what would those be? What are the variables in map coloring? Yeah. Countries, good. And then, so we're assigning values from the domains to the variables. What are the domains? Colors. And then what are the constraints? Right, yeah. Colors can't touch. Or no two adjacent countries can be the same color. We'll see a lot more examples of these, and you'll get a more intuitive understanding for how to take a real-world problem and model it as one of these. But the key idea is these are the three pieces. Variables that you have to assign some value to, domains, which are the sets of possible assignments to each of those, and constraints. There's our map coloring guy again. So we're going to see general purpose algorithms for CSPs that are special case, special versions of the search algorithms, much more powerful in this case. Now we already just did this. We had we had variables, our countries. Oh, geez. Sometimes my iPad thinks that I'm trying to close this. Variables, countries, domains are colors, and constraints can't be touching. Okay. So the next question is, I keep saying that this is a special case of a search problem. What do I mean by that? Well, remember a search problem has three parts: states, successor function, and goal test. Also a start state, we'll do that last. So we need to figure out a way to frame this problem in that way. So this is really not easy to see right away, but the way that we can do this is by defining a state to be a partial assignment to variables. Partial assignment. So an example of a state in this search version of solving CSP, this search view of a constraint satisfaction problem, would be having this country set to blue and all the others still unassigned, or this country set to blue, this one to red, and this one also to red. Now in this case, we know we're not going to find a goal if we keep searching with those assigned that way, but that's another state, a partial assignment of values to these variables, values from the domains. So with that state idea in mind, what would be the successor function? Yeah.
Would it be all the continued partial assignment?
Yeah, it's basically one step forward. A successor of a state is one where we take this assignment that we have right here and assign one more variable. So the successor function is assign an unassigned variable. And then what would be the goal test? It needs to be a function that takes in a state and says, yes, this is a goal state, or no, it's not. We need to keep searching. What would that look like in this case? What was that? Is the map full? Okay, that's one piece of it. Right, so the two parts are, is the map fully colored, and are any constraints violated? So complete and no constraints violated. And what would be the start state? What was that? Yeah, exactly. An empty assignment. Nothing is assigned yet. So let's think about this. Remember that any of our search algorithms, once we have it successfully framed in this way, is going to take us from that start state, nothing assigned, and keep searching and searching until we find a state that satisfies that goal test. So start state, assign one unassigned variable. That could be this blue that I already did right here. And then assign one more unassigned variable. That could be this red, and then this red. And if our algorithm is not paying attention to the fact that this is CSP, it might keep searching along this branch and say green here, run the goal test. Well, that's not a goal state because it is complete, but there are violated constraints. And so it would go back up in the search tree and keep searching like that. We're going to see an actual demo of what our search algorithms from yesterday do on CSPs pretty soon. First, I want to talk about a quick distinction between search problems we've seen so far and what we're trying to do here. So first of all, there's a very specific type of environment that we've been dealing with, and that's where there's a single agent. So we haven't really talked about problems where there's Pac-Man and there are ghosts chasing after him. That will be next week when we're talking about how to plan when you have an adversary who's trying to thwart you at every move. Deterministic actions, which means when you take the action in a Pac-Man board, go right, you know that in the next state, Pac-Man will be one space to the right. There's no uncertainty about what the result of your actions will be. Fully observed state, which means there's not any part of the environment that you can't see and you have to guess what's there. You can see all the information that's relevant. And discrete state space. So that, I keep using the Pac-Man example because it's helpful here. That would be, in Pac-Man we have coordinates for every position where Pac-Man could be. He's at position 2, 3, moves to the right, he's at 3, 3. And then to contrast with that, you could have a real world example with pathing where a robot's trying to get from here over to there. We don't really break up the world into discrete chunks. It's a continuous space that it has to move along. And you can imagine that the algorithms we've been using so far don't directly really handle continuous state spaces. So these are the kinds of problems we've been trying to solve. Planning. And in a planning problem, you know what the goal looks like. Pac-Man needs to get from this side of the board to that dot over there, but you don't know the path to get there, and that's what you're trying to figure out. To contrast with that, and what we're going to be talking about with CSPs, still a search problem, but a different kind of search problem in terms of what we want to get out of it. Identification. So here, instead of knowing where the goal is and not how to get there, this time we don't really care how we get there. We just want to find a goal. To make this concrete, think about CSPs. Any goal state is just any satisfying assignment to all of those variables. We don't really care about whatever things we tried on the way to get there. We just care about finding that end result. And these guys are another illustration. You could have the museum robber robot who knows exactly where the gem is and just needs to figure out a way to break in and steal it. And then the detective robot who's hunting after him doesn't know where the gem is, trying to find it. Once he does find it, it doesn't really matter what he did before getting there. He's found his goal. So here are some examples. We've been seeing a robot painting a map. Now we're going to actually talk about these and give it an explicit CSP representation with domains and variables. We're going to go through this and a bunch of other examples. Some of them will be familiar, some will be new, but you'll see the applicability of the CSP model. The idea here is not just to see that CSPs can be applied to all sorts of different problems, but also to start to get a feel for how to take some problem you're trying to solve and realize that it can be formulated as a CSP. Because once you see that, and once you make that formulation, we already have algorithms to solve it really quickly. So we already talked through this. Variables are all of the countries. Now they actually have names. And it's territories, not countries, because we're in Australia. But the domains are red, green, and blue. And the constraints are adjacent regions must have different colors. So we're going to talk about two different ways to represent constraints in code, implicit and explicit. So an implicit constraint is one that behaves kind of similarly to the way we've been talking about a goal check, where it just takes in two countries and is a function that tells you, yes, they violate a constraint, or no, they don't violate a constraint. So what would a function that takes in two countries and the colors assigned to them tells you that be for this problem?
Just said the constraint was violated, two colors were passed and then the constraint wasn't violated.
Yeah, exactly. An implicit constraint is just take in the two neighboring states, and if they're the same color, it's violated. So the constraint is WA not equal to NT. Now, the reason I phrased it that way might become more clear when I talk about explicit constraints. So an explicit constraint is where, for a pair of variables, you just have a set of all of the possible assignment tuples to both of them. So in this case, if we were considering Western Australia and Northern Territory, a pair of adjacent variables, the set of all possible things that they could be without violating a constraint would be red, green, like they are now, red, blue, but not red, red. That's the idea here. So that's what an explicit constraint looks like. And a solution, now, because we don't really care about a plan, a way that we got from the root to the end, the solution that we're going to take is just what our final state is, where we end up, which is a satisfying assignment to all of the variables that doesn't break any constraints. An example here would be this. So constraint graphs. What are we looking at right now? Well, if we consider the map that we had before, this is a graph where every node in the graph is one of the variables, and there's an edge between them if they're touching on the map. More generally, a constraint graph is just going to be a graph where the nodes are variables, like here, but the edges represent any kind of constraint that is between two different variables. So you can imagine that maybe this constraint right here is if we had some other problem we were trying to solve when coloring the map, not making them all different. This could be they have to be the same color, or if one of them is blue, the other has to be green. Any kind of constraint like that. And so this is just an abstract representation that, similar to search state graphs and search trees yesterday, is going to help us examine how these algorithms run. You'll notice that the way I just defined that, where an edge represents a constraint between two variables, I've only allowed for you to have constraints that are on two variables. You can imagine for some other problem you might have a constraint between three things. Like, for example, imagine if these three countries were not touching, but you wanted to make sure that all three colors were somewhere on the map. And in this case, there's not that part of the map. Then you would have the constraint that all three of them must cover every color at least once. We'll see more examples in a second. And like I said, this is going to be a useful model when we're looking at how these search algorithms run, because we're going to see mostly demos running on just kind of an abstract constraint graph like this. And if you have a feel for what it looks like to take your actual problem and draw a constraint graph for it, then now it's in a familiar form that you know how to solve. And that's, yeah, the algorithms generally do that as well, is they construct this graph and exploit the structure in the graph. So here's another example of a constraint satisfaction problem. N queens. Who has seen this puzzle before? A few people. Okay. Well, the game here is basically you have an n by n board, chessboard, and your goal is to place n queens on squares on the board so that none of them are attacking each other. And if you're rusty on chess or don't know the rules, queens attack like this, along any row, along their column, and along the diagonal. So this is a solution to this problem where we have a 4x4 board with 4 queens because no queen is in any other queen's line of sight. Like that. And I won't do the last one. This is kind of an interesting puzzle to solve as a human, but it's often used as a benchmark for testing how well these CSP problem algorithms do. And when we were talking about benchmarking, sometimes some really optimized algorithms can solve this for 20 million queens. And we'll see actually the algorithm that does that at the end of the lecture. There's some battling queens. So now our goal is to formulate this as a CSP. There are a couple different ways we can do this. So here's the first idea. We need to know for every square whether or not there's a queen there. So our states are going to be, our variables are going to be all of the positions on the board. Variables x, I, j. With that in mind, what are the domains? So for every square, we're trying to determine whether or not there's a queen. What are the things we can assign to each square? True, false. Yeah, exactly. Yes, there's a queen there, or no, there's not. And so that we're going to represent that as 0, 1, true, false, yes, no, any of those work just as well. And then we need to talk about the constraints. What are the constraints?
The queens can't be in a straight line from each other?
Right. Yeah. The queens can't be in a straight line from each other. And we need to somehow express that in terms of the variables xij. So here's one way to do that with explicit constraints. For every single ijk, so all ijk that define actual positions on the board, every 2 that are in the same row, so they have the same I, but j and k, their horizontal position is different, comes from the set 0, 0, 0, 1, or 1, 0. What's missing from this set?
1, 1.
1, 1. And so 1, 1 would mean in this row, both of these squares are occupied. So as long as that is not the case, in other words, it's in this set, there are no queens sharing the same row. Then we need to do the same thing for the columns and for the diagonals. And it gets a little bit messier, but you get the idea. Is that all of the constraints? Yeah? So let me give you a solution to this problem. Every single xij is 0. That satisfies all of these constraints, right? Because 0, 0 is in all of these sets. But we don't have any queens on the board. So what's missing? What constraint do we still need? Yeah?
The sum over all xij's is n.
Yeah, exactly. We need to have at least, well, exactly n of these different positions are occupied by queens. And since we represented it with 0s and 1s, we can do that succinctly as the sum of all of the xij's is equal to n. 1 for everywhere where there is 1, and 0 everywhere else. So let's talk about a different way to do this. Actually, does anyone have any ideas for how we might formulate this in a different way as a CSP? A different idea of what the variables and domains are. We're doing pretty well on time, so I'm actually going to give you 30 seconds to think about that. Talk to your neighbors and try to figure out a better, or at least a different representation of this problem.
Maybe just know any extra line. So, maybe there's no any X, Y, and from just like in every one of them, everything. And basically everything again is interesting. Separate queen by one down duo. Because essentially that's what you would do.
All right, let's bring it back in. Does anyone have ideas they think are pretty good? Anyone in the back we don't hear from very much? No? Okay, I think you had your hand up first. Yeah.
Can we use n variables?
Okay.
And each variable range from 1 to n, and the variable represent the position in the column in the corresponding. Because we must have n queens, and each one must occupy one column, and so one column we will only have one queen.
Yeah, that's exactly right. So now, here's the key observation. In any solution to the n queens problem, you're going to have, oh geez, come back. You're going to have, sorry about that. In any solution to the n queens problem, you must have one queen in every column, right? You can't possibly have two queens in one column. That would violate a constraint. And there are exactly as many columns as there are queens. So what can we do? Well, now say instead of for every single square, is there a queen, is there not? It's for every column, where in that column is that column's queen? So now, works just as well with rows. That's what we've drawn here. So in the first row, our variable is q1. Where is the first queen? And the answer is, it's in the second position. So the assignment is q1 is 2, q2 is 4, q3 is 1, and q4 is 3. What are the constraints now? Let's think of an implicit representation, because those are usually a lot easier to think of as humans than the explicit ones. You have an idea? What was that? Okay, the one queen per row constraint that's part of the problem is actually already being expressed by the way that we're doing these variables, because it's never going to assign two numbers to one variable. There's already one queen per row. You have an idea? Okay, yeah, no two of them can have the same number assigned to them. We can come up with a more general representation of this and all of them. If you were unpacking it into a bunch of different constraints, that would have to be one of them. But since we're doing it implicitly, let's just go with the way we think about it as people. For all ij, the queen in row I and the queen in row j are not threatening each other. So part of that is what you said, where they can't be in the same column. But that also means they're not on the same diagonal. As an explicit constraint, it would look kind of like this, where notice that we don't have 1, 1 as a possible value, and we don't have 1, 2, because then the first queen and the second queen would be conflicting along a diagonal. Here's another example, probably more familiar. And in fact, if you've done this a lot, you might have already been thinking of this, because the rules to this game are kind of defined the way we define a CSP, where the game Sudoku is, for every one of these squares that isn't already filled in, you need to draw a number in it from 1 to 9 so that there are no 2 of the same number in one row, no 2 of the same number in one column, and no 2 of the same number in one 3x3 region. That is a CSP. Variables are the open squares, domains are the numbers 1 through 9, and the constraints, there are 2 different ways you can write it. I just said the pairwise inequality constraints. This one can't be the same as what's here, 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 etc. Can't be the same as what's over here. And then it also has to have a different way of formulating the problem is everything in this row must be different, this column I mean, everything in this row must be different, and everything in this 3x3 region must be different. As a quick note about constraint graphs, if we think about this in the second way, where it's these all diff constraints, those are not binary constraints. Those are constraints on a bunch of variables all at once, all of these. And so what we do is we draw something like this, where you can imagine that each one of these open squares is a node in our constraint graph, and it has an edge to these squares up here. We draw extra nodes in the graph where each node represents a constraint, and then every constraint that it affects is connected to it. And this way, we can reason about it in a similar way, where anytime we assign something to here, we now have to worry about it violating a constraint with any of these things that its constraint right here is connected to. This is not going to come up a lot, but if you are wondering about how constraint graphs handle non-binary CSPs, we add nodes to represent the non-binary constraints. So, step back, we've seen some examples, and think about the high-level picture of CSPs. All of the examples that we saw lie in this very small subset of what can be reasoned about in this way, and these are all of them that we're going to look at in this class. We'll see why in a second. They kind of fall into other domains when we leave this. But discrete variables. So we're talking about assign the color red to this country or put the number 2 in this box, these kinds of things, where you might instead have continuous variables. And that would be like if you're trying to schedule start and end times for a telescope. That's one that we'll see in a second. So discrete variables and finite domains, where for Sudoku, it can be 1, 2, 3, 4, 5, 6, 7, 8, 9. For the map coloring, it can be red, green, blue. You can imagine that for some problem like scheduling, where you need to give everyone some amount of time on a computer, but they can't overlap at all, and you want everyone to line up on the hour, something like that, that's still a discrete problem because you need to decide which hour each person gets. But it's not finite because you can give them any hour on into infinity. So this is the small set of all possible things that can be viewed as CSPs that we're dealing with today. Just quickly, a note about complexity. And this is not prerequisite material, and it won't be tested on, but if you're familiar with complexity theory and Boolean satisfiability, SAT or 3-SAT, and the idea of NP completeness, that's another CSP, because the goal in Boolean satisfiability is you have a bunch of binary variables that can be true or false, and you have to assign true or false to them so that they satisfy a bunch of clauses. That is a CSP, and the fact that a CSP solver then must be able to solve satisfiability means that CSPs are NP complete. Taking a step back from complexity, slight extra material there. Why is this O of D to the N complete assignments? Well, if we imagine an arbitrarily large map, so something that Looks like this, and there are a whole lot of countries in here. Then if there are 6 colors, let's just say D colors, there are D options to go right here, D options here, D, D, D. The number of total assignments to all of the variables is O of D to the N. And so that's the size of the search space that we're considering. Because remember, any of those assignments is a state in our search space. Hinting at why the search algorithms we've seen so far don't work all that well here, because that's a huge search space when you have a lot of variables. And continuous variables, like I said, start and end times for a telescope, or if you don't have the constraint for a scheduling problem that you want it to line up on the hour or something like that, also continuous. If you're interested in talking about these problems, they come up all over the place, and you see them a lot in theory classes like 170, 270, and in optimization classes like the 127 series. It's constrained optimization. So that's varieties of different problems we're trying to solve. Now this is different varieties of constraints. So the first is how many variables it affects. We talked about the difference between binary constraints and higher order constraints, Sudoku row constraints. Another example of a higher order constraint would be in the first formulation of n queens, where we had that sum of all of the positions has to add up to n. That's another higher order constraint because it affects every single position, much more than 2. What we didn't mention yet is these unary constraints. So a unary constraint is much simpler than those other constraints. It's just this particular variable cannot be this value. And when you're actually doing these algorithms, you can either have some code as part of your algorithm that handles unary constraints during execution, or there's another way that you can handle this, which is just say, well, if South Australia can't be green, then green is not in the domain for South Australia. And that's basically you've defined a new CSP with no unary constraints, but reduced domains. And then another thing we won't touch on very much now, but that we'll get back to later, is preferences. So we've only talked about hard constraints where this cannot be the case. These must satisfy this condition. This is where you would prefer that this is the case, and maybe you assign some amount of importance to the fact that this is satisfied. But you can still find an assignment that doesn't satisfy this and be happy with it. But you would just prefer that you could. We'll talk about that a lot when we get into decision theory with Bayesnet and Bayesnets and have more background for talking about reasoning under uncertainty. So here are some examples of real-world CSPs. Timetabling, one I'm sure you have experience with. Signing up for classes, that's exactly what that is. You can't have 2 classes at once. You have some major requirements you have to fulfill by the time you graduate, all these kinds of things. And so that's probably the one that hits closest to home. There are a lot of other ones. We also have hardware configuration, and this kind of goes hand in hand with circuit layout, as now our variables are some position in a specification, and our constraints are that this part has to be connected to this part, and they can't be in the same position, all these kinds of constraints. You can use a CSP solver to actually design something that fits this specification. Transportation scheduling, if you need buses to be running at some maximum interval so that people can get from point A to point B according to whatever needs they have. That's another example. Rostering is an interesting one where if you have a lot of jobs that need to be fulfilled and a bunch of people who are capable of doing some subset of those jobs, then you need to, well, you can think of that as a CSP. And that's one where in operations research, that's usually the way those problems are solved. Yeah. We'll jump past these. If you're interested in any one of these, you can talk to me about them later. But right now, let's get into solving CSPs. So we talked about what they are, how to think about formulating problems as them. And I mentioned the standard search formulation. Quick recap. States are partial assignments, and we start out with an empty assignment and proceed by picking some variable assigning some value to it, and now our new state is what we had before, but with that one extra variable assigned. How would BFS handle the map coloring case for Australia? So I'm going to give you another few seconds to think about this. Remember, we're starting with an empty assignment. What path does breadth first search trace out? Think for 30 seconds. Feel free to talk to your neighbors. All right, just a little bit of time to think about that. Hopefully you have some idea. Can I get someone to raise their hand and volunteer an answer? What's going to happen when we run BFS? Anyone? Yeah.
You just choose a start node, and then you would expand all the neighboring nodes of that one, and in turn just expand each of those neighbors.
Okay.
And each step of the way, make sure that the constraints are violated.
All right. So I like that answer because you've looked ahead to a later part of the lecture. You've made BFS smarter than it actually is. What's going to happen, like you said, we are going to expand nodes, but it's important to make the distinction between expanding nodes in a search tree, and now we have this other graph, a constraint graph. Breadth first search is going to build up a search tree, right? We start out with our root node at the top, the empty set, and then we're going to pick one variable and assign something to it. That's one of the start state's successors, because remember our successor function is just to pick a variable and assign to it. And what are the other successors? Western Australia could also be red. Northern Territories could be green. There are all sorts of other choices we could have made. Basically, any assignment of one color to one of these countries is a successor to that root node. So a bunch of stuff on both sides. You want to be careful about getting mixed up between this constraint graph and the search tree, which we're building up right here. Breadth first search expands the root node and then goes in level order in the search tree. What's level order in the search tree? The first thing it's going to do is check all of those states. In other words, first thing it's going to do is try assigning Western Australia to red. And then what's next? Well, undo that. Let's assign it to green. Okay. Undo that. Let's assign it to blue. Undo that. Let's go red at Northern Territories. And on and on. So what's going to happen is it's going to try every single coloring of one variable, and then every single coloring of two variables, then three, on and on. It's not going to ever even try to color all of the variables until it's expanded the entire search tree. So, yes, very bad. This is, I mentioned when we were doing uninformed search a couple days ago that we'd run into some problems where we know enough about the structure of the problem to say we don't know exactly what a solution is, but we know it's at the bottom of the search tree. So down in here, we don't know where in here an assignment that satisfies all the constraints would lie, but we know it's somewhere in here and it's nowhere up here, which means depth first search is going to do a lot better because depth first search is an algorithm that goes straight to the bottom. So let's jump ahead to DFS. What would DFS do? Without giving you some time, just quick raise of hands now that we've seen that search tree. It might be easier to conceptualize. Yeah, that's it.
Start at Western Australia and try out random assortments to see if they'll eventually have it.
Right.
Probably goes all red first, right?
Yeah, so that's a great comment. So what's going to happen is we're going to assign something here, say red at Western Australia, and then we're going to do another another assignment, expand our partial assignment, because we're going deeper along this path in the search tree. If you have some just random tie-breaking scheme, then you might end up with something pretty good, and you might get where you want to go really quickly, like that. But typically what we do, or at least in the worst case, to illustrate why depth-first search is not quite what we want yet, we're going to go with an alphabetic tie-breaking scheme. Well, no, not quite alphabetic, but blue, red, green. So anytime there's a tie between nodes in its search tree on its fringe that it could expand, it'll go with assigning blue before it'll assign red, then green. So actually, that. And it may seem like I'm creating problems where there aren't any, but this is to illustrate what the worst case is and why depth-first search does not perform all that well. Let's see a demo. If I can find it. Yes. Okay. So this is basically the map coloring problem, but with a different constraint graph. Each one of these circles needs to become one of those three colors, and no two circles that are connected can be the same color. Okay, so we're going to do, not backtracking, naive search. It's called naive search here. This is just normal depth-first search. And it's going to do exactly like I said. Tie-breaking order is blue, red, green. So it'll first go all the way to the bottom, assigning everything to blue. Now it has no more successors along this branch, so it'll go back up the tree a little bit and try assigning that to red, then green, then red there. And you can start to see what's happening. Basically, it looks like it's a base 3 counter, something like that, not doing anything much more intelligent than that. So what went wrong? If we are actually trying to solve this problem, clearly we know as soon as we're at this point right here, nothing down this path could possibly be a solution. So this was hinted at when we were talking about breadth-first search, that we should be able to say, if we violated a constraint, stop searching this way. That's pointless. You'll never find a goal. Backtracking search. That's what backtracking search is we just take the search algorithm we had before and add that optimization. And there's one other minor optimization we'll see in a second that you've probably already been thinking in your heads, but we need to make concrete. This is the basic uninformed algorithm for solving CSPs. What I mean is, no one ever uses depth-first search, breadth-first search without this optimization to solve these. And most algorithms anyone does use, they're based on backtracking with various tweaks and optimization. So here's I'm going to do these in the other order, actually. Check constraints as you go. That's what we were just saying, where once you have two blues next to each other, don't keep assigning things, just backtrack right away. Give up on this search branch. And then the other idea is one variable at a time. This is a more subtle point, but the idea is just, remember when we had that search tree with the empty set here, and we could have said Western Australia equals red, ... Northern Territories equals green. We're going to make the possible successors a little bit smaller, where now instead of that, when we're at no assigned variables, we're going to pick one variable. That's the one we'll assign next, and our different successors are just what we could choose as the color. And then G. And this makes the branching factor a lot smaller. It's called backtracking search, and with nothing more than this, we can solve n queens for about n equals 25. Yeah, you had a question? Good question. So what if, maybe not at the root here, but somewhere farther down the tree, we had some assignment right here, ... and we chose next to assign Western Australia, but it had nothing that it could successfully be assigned to. Well, that's actually something we'd want to know right away, because if there's nothing Western Australia can be assigned to right now, then that means no matter what else we assign later, Western Australia is still going to have that problem, which means we're already down a search branch that's going to fail. That's actually, in fact, we have a heuristic we'll talk about a little bit later if we're trying to notice when this happens. And if there is any variable that could possibly fail, find it as soon as possible. So that's a great question. So here's an example, backtracking. Our start state is nothing assigned. Expand to children. Assign Western Australia, that's the one we've chosen first, to be its 3 possible successors. Now we're going to pick arbitrarily. I'm going to go with the red one on the left. Expand its successors. This time we choose Northern Territories again as the next one, but it only has 2 successors. The third one, which would be over here and have red for Northern Territories, don't even bother adding that to our fringe because there can't be a goal in that direction. So we have a search tree that looks like this. And basically, a little guy who tells us every step along the way, you've already failed, don't keep looking. So that's backtracking. Let's see if there are any ways that we can stump backtracking. First, actually, before we watch it get stumped, let's see it do well. Give it a chance. Yeah, it's gonna, as you can see, maybe I should go slower. Well, there you go. It solved it. I'm gonna do that in slow motion now. See, we didn't assign blue there. Remember the tie-breaking order is blue, red, green, so it's gonna go blue. Blue couldn't go there. Blue and red can't go there, so it'll be green. And now there's nothing it can be, so it'll backtrack now, instead of going all the way to the end before realizing that it has to. And then now we know that's not green, and that's the only thing it could have been with red there. So we'll try green there. And then that's the kind of reasoning that the algorithm is implicitly doing as we search through this whole thing and get to the end. Yeah? If we didn't apply ideal 1, where you're fixing which variable you're going to assign next, then there would be other successors to this root. I won't draw all of them, but here's my little Australia. And now you're assigning something else. So say you're assigning this little one down here to be all its different values. And those would all be successors to the root. Good question. This is still a pretty small graph, though. So let's up the difficulty a little bit. Oh, wrong one. Same problem, but a lot more variables and a bit more convoluted structure of the constraints. So I'm just going to let it play, and I'm going to let it go pretty fast. Uh-oh. We're kind of stuck in the same hole that we were with depth first search the first time. So already we're seeing we've maybe tripled the size of the problem, and we've hit something that backtracking alone is having trouble with. Now I want to go through that in slow motion and see if we can see where the problem is. So first assign blue, then red, blue, red, blue. That's going to be red, on and on. And now we assign that green. We see our first green. Does anyone see the problem? I see pointing. Yeah, the top left one, exactly. So now we've already basically made it so that there's no way we can assign anything to this variable up here, right? It's connected to a blue, it's connected to a green, or a red, and it's connected to a green over here, which means we've failed. This branch is not going to find us a solution because there's nothing we can assign there. But with the algorithm as we've described it so far, it's not going to realize that until way later, because in the order that we've chosen, that variable is much later. So we're going to have to backtrack probably millions of times until we get back to actually changing what's right here. Here's an idea for how to fix it. It's called filtering. So the idea behind filtering is for variables that you haven't assigned yet, keep track of all the remaining values in their domains, values that don't yet violate any constraints. Here's what that would look like for a small example, the map coloring example. The domains of every variable start out as all three colors, and then we're going to assign one, and this algorithm forward checking, which is a type of filtering, just says when you assign one variable, cross off everything that is now violated on all its neighbors' domains. So we assign Western Australia to be red, and then red is going to be removed from the domain of NT and SA because it's touching both of those. And now we have this. Western Australia has been assigned right here, and these, should not use red, are now gone. Step through a little more. We could have arbitrarily chosen Q to assign to next, pick green. What's the next level going to look like? Well, we're going to see green disappear from here and here. Oh, and NSW. So we have this. And then assign blue down here. Now we're at this. Notice that SA, South Australia, has an empty domain. Bad choice of color. Empty domain because we're talking about this variable. We've already had a red right here. Actually, I don't need to draw that on there. A red right here, a green here, and a blue here. There's nothing that could go here. Empty domain means we can't possibly find a solution. So let me show you what forward checking looks like on this example. So now you can see it's a similar kind of diagram where all of the variables have the three colors they still could be visually represented here. We're keeping track of them. So as always, sometimes that happens. As always, we're going to start with blue in the bottom left and see that blue disappeared from the domains of the neighboring ones. Red disappeared up there. We'll keep, nope. Spoiler alert, that shouldn't be on. We'll keep doing what we were doing before, except this time we get here. Forward checking tells us we have a variable with an empty domain. We can't find a goal. So we backtrack right there instead of way later. So that's a massive improvement. It solves its problem. It only has to backtrack from here back to wherever it needs to so that this can be something other than green, much less than we were doing before. If I let that play a bit faster, we managed to actually solve the problem. So that's great. We still did backtrack a lot, so we're going to try to think of ways that we can improve that. First question.
Didn't that cause a problem with memory issues when you're forward checking on a whole lot of random variables?
Yes. You do run into a pretty, if you have big domains, you run into a pretty serious memory overhead for doing it this way. And if that is a problem in your particular problem you're trying to solve, you can come up with some tweaks to it, like not explicitly keep track of all those variables and just check the ones as you go, things like that. You're right, though, that we do incur some extra time and memory cost for keeping track of extra information and checking extra things at every step. So the next idea is ordering. This is that heuristic I mentioned earlier, already basically discovered, but if we already have that one variable is empty, we don't want to keep searching. And similarly, if we're going to, as a result of what we've already done, end up in that situation, we'd rather it happen sooner rather than later so that we can start backtracking while we're still at the bottom of the graph rather than get all the way to the top before we realize there's a problem. So here's the idea: minimum remaining values. And if you've played Sudoku before, I want you to have that in your head while I'm talking about this, because it's a pretty natural application of this. When you're assigning values to these variables, we haven't really talked about how the algorithm is going to decide which variable to assign next. So far, we've just been doing it arbitrarily. As far as starting out, we will continue to do it arbitrarily. Western Australia is first. But now, once we're here, we have a bunch of different options. All of these countries. But we saw when we were doing the example of why forward checking is good, that if we go over here and color that blue, or green, color that blue, if we jump over to the other side of the graph, it's much more likely that we're going to end up blocking off stuff in the middle from having any color it could be. So why don't we say, we already know that if there's a solution down this path, this is going to have to be green or blue, this is going to have to be green or blue. That means if these are green or blue, we're done already. So rather than put off what we already know, let's do it right now. That's going to have to be green, that's going to have to be blue. And why min rather than max? Again, it's kind of a fast fail idea, where what remains in the other variables' domains is a result of what we've already done. We have no control over that. So if we're going to end up with an empty domain, we want to find that out sooner rather than later and jump into the ones that are most constrained already. Let's see that in action. Add the MRV heuristic. So remember, when I let it go a bit faster, forward checking without MRV solved it, but it had to backtrack quite a bit. Now let's watch this. First assign blue. Now it's going to go to either of those ones that have only 2 before it gets to anything else with 3. And now we know that if there's a solution down this path at all, it must have a green up at the top. So let's assign a green. Oh, let's assign a green right there. And then it's going to keep going. There are some variables that have only 2. Now we're kind of chasing where there are these problems, more or less, where we're constrained already, following those. And that way, we'll find out sooner rather than later if what we've already done is going to lead to a failure. Turns out, as we keep going in this direction, for this problem, we can solve the whole thing without backtracking once. So it's a massive improvement based on a pretty simple idea. And there are plenty of other improvements to backtracking. We can't talk about all of them here because you can imagine all sorts of applications that make people money from that list of real-world problems that I talked about. A lot of work has gone into making these algorithms fast. But that's all we're going to talk about for backtracking today. The next thing I want to talk about is a different way of approaching these problems: iterative improvement. So what we've done so far is start with an empty assignment and work our way incrementally up to a full assignment. Now what we're going to do is start with just any full assignment, not even bother with the constraints. If we could just start with one that solves it, we'd be done. So start with some assignment to all of the variables that probably violates a lot of constraints. And then what we're going to do from there is basically find all of the problems that are in this assignment we've chosen and try to fix them one by one. And as we fix one, we might introduce problems elsewhere, but generally we can move more or less in the right direction by just doing this over and over. So our search idea here is now not the successor is to add another assignment in our partial assignment, but to take our full assignment to all the variables and change one of them. So states are now full assignments, successors are change one of them. And the algorithm, very simple. Find one variable that's violating a constraint, change it to whatever in its domain violates the least constraints. It's called min conflicts. And if you're familiar with hill climbing from any theory class or anything like that, it's hill climbing with your heuristic equal to the number of violated constraints. If you're not familiar with hill climbing, we'll cover it in a little bit, and then we'll come back to this. But an example where this works really well is n-queens. So as a reminder, the algorithm is pick some variable that's violating a constraint and change it to whatever in that variable's domain violates the fewest constraints. Applied to n-queens, that means pick a queen that is being attacked and move it wherever in its row. I guess for this diagram we have columns. Wherever in its column it is attacking the fewest queens. And we actually have a demo of that. Should hopefully help. So right now, we're going to start with a really bad assignment. Everything's in the same column. And we're going to, this is the formulation of n queens, where each queen gets its own row. So let's just pick one of these arbitrarily. We're running the algorithm by hand. They're all violating constraints, so we can pick any one of them. And now, of the options that we have anywhere else in this row, which are the values in the domain of that variable, we're going to pick the one that violates 0 constraints over here. And just pick some other one that's violating any constraints. This one, to minimize the number of violated constraints, would be one of these. So let's go here. And we just continue doing this. Done, very quickly. So without any mind toward where we were going up, every time I've done this demo by hand, I was like not even ready to be done when it ended. So it's pretty impressive. And you know how I said backtracking search can solve n queens with 25 queens? Min conflicts can solve n queens with about 20 million queens. So this is actually kind of amazing. It's an even simpler algorithm, and it's not going to have a lot of the guarantees that we have with our search algorithms that we've been talking about, but in practice it works really, really well. Yeah, we'll talk about, actually let's talk about that right now. So is this algorithm optimal in this sense? Yeah, so for this problem, remember, optimal is a bit of a weird notion for CSPs because all of the solutions are equal to us. We just want to find some solution. So optimality is not really a notion we're concerned with. What about complete? Is this complete? Yeah, so it turns out that with some really weird configurations that we won't go through right now, but you can figure out later, you can actually get stuck going back and forth between the same states, or get stuck in a cycle where you're not improving at all. We'll see kind of a more general view of these kinds of algorithms where it might be a little more intuitive, but for now you can imagine if you have some really bad tie-breaking strategy, some really bad tie-breaking strategy. Let me start this over. Like, see this one, say our tie-breaking strategy is whichever one's on the top. That means this one is violating a constraint. All of these are equal in terms of the number of constraints still violated, so we move it there. Well, what's the top variable that's still violating a constraint? The same one. We move there. We're stuck in a cycle. So naive n queens, as we've defined it, in the worst case is actually incomplete. You can get stuck in cycles. There are some improvements that you can make to that, especially probabilistic ones, where it ends up doing quite a bit better. But we're not going to talk about that today. Quick summary of everything we've talked about with CSPs. Constraint satisfaction problems. They're a special kind of search problem where now instead of trying to find a plan to get from start to goal. We're just trying to figure out where the goal is. And when we say goal, we're talking about a goal test that says we've assigned a variable to every single one of these, we've assigned a value to every single one of these variables, and none of these assignments violate any constraints. The basic solution that we went through and looked at a couple of improvements to is backtracking search. And those improvements specifically were filtering, that forward checking algorithm that's very simple. You just, every time you assign something, remove that value or remove any conflicting values in the neighbor's domains. And ordering, which is minimum remaining values heuristic. If you have a bunch of different variables that you can assign next, pick the one that is already most constrained. And then iterative min conflicts, the one we just saw, often very effective in practice. So here's a more general idea. We're kind of stepping out of CSPs. We're going to use min conflicts as our transition into this, because min conflicts is a special case of this much more general idea, local search, that is super useful in all of computer science, actually. This is going to come up. In fact, once we go through this, you'll probably realize that some things you've done before in your intro classes are special cases of this. And so we want to have a general sense of this idea, local search, where before we were talking about being able to see the entire state of our environment and taking actions that we know that what their result's going to be. We can exhaustively search the whole space. We keep a fringe of all the next things we want to explore. Now instead, we're going to imagine, rather than a simulation in our head of the entire game, we are right here. We can see what's right around us. We have actions to go there, there, and there. And we know we're trying to get to that side of the room, so we're going to go that way. Now we're here. We can go there, 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 or there. We're going to go that way. The difference here is rather than having a fringe in this simulation in your head of the environment with all of the different trajectories you could take, you're actually following a path just based on where am I now, where can I go next. If you remember from the second lecture, I was talking about reflex agents. This is an example of that. This is where reflex agents actually do really well. The punchline, the quick reason is some environments are so difficult to work in that no other algorithms work well, so we just do something simple. Yeah, question?
Is the application of this gradient extent?
Yes. And I'm going to get to that one, actually next slide, that lots of people may argue with me, but what may be the most important algorithm in computer science is gradient descent, which is a hill climbing algorithm. Like what I was just describing, where you have your robot. He's right here on the hill. And his goal is to get as high as possible. If, due to some aspect of your environment, it's too difficult to run the entire search, like you don't know what's way ahead of you, that's generally the reason, is you don't know the entire contour of the environment, then you can just go up. You know that if you're trying to get as high as possible, go up is a pretty good rudimentary strategy. So that's why the robot is moving in this direction. So yeah, running through that algorithm, start somewhere. You can just pick a random position to start, and then move to the best neighboring state. Now you're in that state. From there, move to the best neighboring state. And as you keep going, you will ultimately end up at some local maximum. So yeah, you're going to keep going. If this robot were running the algorithm, step up, now he's here, step up a little more, here, here, until the robot finally gets here and sees that nowhere around the robot is there somewhere that's higher. He no longer can go up. So he's going to terminate and find this. So you can see what's wrong with that. We want to go as high as possible. There's somewhere that's a lot higher. We didn't get there. We got stuck. So this is not optimal because this is an algorithm that's going to terminate with a solution. The solution in this case is this position that the robot has found. That is not your optimal solution, because the optimum is up here. And can it be complete? I see some shaking heads. Here's my hint about this. We just saw an example where it was not complete. And the reason, in this more abstract view, imagine if our robot started right here and ended up going up to this point. Now, if you have a termination strategy that says, if I can't strictly increase next to me, then he's going to stop right there, and you're going to have suboptimal performance. Or you could have a strategy that says you're also willing to explore flat ground, because you might find a shoulder like this, where if you keep going in this direction, ultimately you'll find the optimum. And so certain implementations can be complete in the sense that they'll always terminate. You'll find a local maximum. But a lot of implementations, if you're willing to handle this shoulder case and not give up because you found a plateau, then now you've run into incompleteness because you might just end up wandering back and forth around here. And if you can imagine this being a much more high-dimensional space, it's not quite so obvious that you can just not go back in the direction you've already been. There's an infinite number of different directions that you can keep searching if you have a plateau region like that. But what's good about it? It's easy. That's really the answer. It's effective in practice because a lot of problems that we want to deal with, even if we are having trouble formulating them as complete search problems where we know the entire state space and can deal with them perfectly, you're still going to have environments that might look like the hill looks like this, or maybe something a little bit more like this, where the suboptimal solutions you could find aren't that much worse. So we're not optimal, we're not complete, but it's easy to implement, and it works in a lot of different environments. In a lot of those environments where it doesn't perform optimally, it's still not that much worse than optimal. Here's a kind of diagram you're probably going to see a lot more in all of your computer science career, but especially when we start talking about gradient descent for deep learning later in this class. You have some function you can vary along the x-axis. We'll call that the state space for now, using the language we've been using this week. And then you have an objective function along the y-axis that you're trying to maximize. So when it's visualized this way, it still is very literally hill climbing because we're looking what's right around where we are currently. So if we're right here, go up, we're going to end up here, go up, etc. until we're up here. I think we already talked about these different cases of shoulder and local maximum. In case the terminology is not fresh from calculus, global maximum is the actual optimum point on your entire objective function, the optimal solution. And we can also have flat local maxima like this. So if you have your algorithm willing to continue along a shoulder, then now flat local maxima is a weakness you've acquired, because you might keep being optimistic and thinking you'll eventually find something that goes up, but in fact, it just is flat here and goes down on the other side. Question?
Would it be possible to use iterative improvement as the tiebreaker? So just test for a small area, and if there is a better option, then continue on with the local search.
Test a small, so if I'm...
So it's like if you're on the shoulder, you can tell just simulate the area that is that small shoulder portion, and not have to deal with all the extraneous data, and see if it can go higher.
I see. So the question is, can you simulate everything that's on the shoulder without looking at the entire function? Am I more or less understanding? So in a lot of problems, yes, you can. And those generally tend to be the easier problems. The really difficult problems where hill climbing is the best we can do, or some hill climbing-like algorithm is the best we can do, we usually can't see that far ahead, or it's very expensive to simulate a large part of the space. So you can imagine there's a function that maps state space to objective. Of course, that's what the objective function is. But maybe it's expensive to compute. The example we'll see later on is the value a neural net gives you. That takes a little bit of time to compute, and so what we're going to do is, rather than try to draw this entire function and circle where the maximum is, we're going to take steps in either direction, like I was saying, hill climbing. But to actually be able to say, where does this shoulder end, simulate the whole shoulder, you'd have to know in advance what that is. The way you'd construct that is you'd have to call this function at a bunch of different points, and that's pretty expensive. All right, we're going to skip this hill climbing quiz. If you want to do that, it's on the slide. I just want to quickly talk about simulated annealing before we go. We won't really talk about any of the theoretical guarantees this gives you, but it's a really cool and useful algorithm. The main problem with hill climbing is that if you start near a local maximum, you will end at that local maximum and be stuck at that suboptimal solution. There's nothing you can do. Simulated annealing injects some randomness into your algorithm, where you say, toward the beginning, you take big random jumps, more or less, with some relatively high probability. Instead of going up, you just pick a random direction to go. You go down, if it's just a two-dimensional case. And then as the algorithm progresses, you become more and more confident that you've been moving roughly in the upward direction. And so the probability that you take the wrong move, go down, is going to decrease. The reason it's called simulated annealing is there's an analogy. If you can imagine, it's easier to imagine for a minimization problem. So imagine instead of maximizing, we're trying to minimize. We take this graph, flip it over, and we're just trying to find the lowest point on there. Our current state is a ball that's rolling around in there somewhere. Hill climbing, now in this reverse problem, would be set the ball somewhere and let it roll until it gets to the bottom. Simulated annealing is set it somewhere and shake the graph really hard, and it'll bounce around a bit, and then slow down with how you're shaking it. And so with this analogy in mind, you can imagine with pretty high probability, while it's bouncing around a lot, it'll end up in that big bowl that ends at the lowest minimum point. There are some theoretical guarantees that make what I'm saying less intuitive and more mathematical, but they're a bit harder to understand. We're not going to talk about them today. So that's everything for CSPs and local search. Thank you.